Geography dictates how a vehicle is built. To absorb highway speeds, engineers rely on multi-link suspensions. To navigate tight urban corners, they use McPherson struts. In the European market, physical footprints are expanding, with new cars growing an average of 1 centimeter wider every 2 years. This physical expansion creates immediate friction with existing urban infrastructure. Wider bodies encroach on pedestrian spaces, and the resulting raised front-end heights carry a 30% higher risk of fatality in collisions. But while physical geography dictates a vehicle's suspension hardware, administrative laws dictate its engine emission behaviors. An identical engine block sold in multiple countries will produce vastly different environmental outcomes. This divergence is the result of regulatory topography, the distinct legal frameworks governing how these engines operate in the US versus the EU. To understand why modern emission systems operate the way they do, we have to reverse engineer the legal codes they were designed to satisfy, rather than just inspecting the engine block itself. The United States and the European Union built their emissions frameworks around different priorities. The US heavily targeted localized air pollutants, while the EU historically prioritized overall greenhouse gas reductions. To control local air quality, the US Environmental Protection Agency applies a technically neutral philosophy to pollutants like nitrogen oxides, or NOx. The US Tier 3 sets a rigid 0.04 gram NOx limit per mile for both petrol and diesel. The Euro 6 standard diverges based on fuel, capping petrol at 0.06 grams, while permitting diesel engines a higher limit of 0.08 grams. Regulators permitted this higher local pollution limit because the EU was heavily focused on reducing carbon dioxide emissions. Because regulatory targets were based on fleet average CO2 calculated by vehicle mass, manufacturers were heavily incentivized to adopt diesel engines, which burn fuel more efficiently than their standard petrol equivalents. By prioritizing carbon dioxide reduction above all else, European regulators established a legal haven that accommodated higher localized nitrogen oxide emissions from a rapidly expanding diesel fleet. Establishing a legal limit is only the first step. That limit is only as rigorous as the specific laboratory cycle used to measure it. For decades, European compliance was measured using the New European Driving Cycle, or NEDC. This graph displays the NEDC's speed profile. Parameters mandate slow, predictable accelerations, keeping the engine's thermal state low and steady. Manufacturers engineered emissions hardware, like lean NOx traps, to operate specifically within this narrow compliance zone. The US relies on a different testing metric, the Federal Test Procedure. The FTP and supplemental USO 6 cycles demand sharp acceleration, sustained high speeds, and air conditioning engine loads. When a vehicle calibrated exclusively for the gentle NEDC curves is pushed into aggressive traffic, the hardware is overwhelmed and engine temperature spikes. Once the engine exceeds those narrow laboratory parameters, the emission controls become ineffective, causing real-world nitrogen oxide outputs to massively exceed legal limits. Manufacturers engineered their vehicles to execute a highly predictable laboratory procedure, rather than to clean the exhaust in the physical world. This operational gap was maintained by the administrative structure enforcing the rules. The European Vehicle Approval Framework originated in 1970 to ensure that national safety rules did not disrupt the free trade of vehicles across borders. Environmental protection was a secondary priority to maintaining a frictionless internal market. Under this framework, an original equipment manufacturer doesn't report to a central authority that can submit their vehicle to any member state. This multi-state option creates regulatory arbitrage, allowing manufacturers to shop for the most lenient regulator. The United States utilizes a highly rigid compliance architecture by comparison. Rather than a network of competing state bodies, the US relies on a single, centralized federal node to evaluate emissions compliance. The Environmental Protection Agency holds a monopoly over the certification process and operates with a primary mandate to protect human health. As a result, authority shopping is impossible in the US market. An administrative structure designed to protect a market inherently distributes authority, creating exploitable gaps that centralized environmental frameworks avoid. This structural divergence also dictates how regulators handle software, specifically defeat devices. These are lines of code or hardware components programmed to disable emission controls when the vehicle operates outside testing parameters. both the European Union and the United States explicitly prohibit the use of defeat devices in their regulatory codes. They also share identical legal exemptions, permitting engineers to disable emission controls if doing so is necessary to protect the engine from severe thermal damage or catastrophic failure. The critical operational difference lies in the reporting mechanism. The EPA requires exhaustive engineering justifications for any auxiliary emission control device, proving exactly when and why the system disables controls. Conversely, the historical European baseline had no such upfront disclosure requirement, leaving authorities completely blind to the engine's programmed behavior. A legal ban on defeat devices is entirely unenforceable without a mandatory administrative mechanism to preemptively audit those engine protection claims. The European emission failures were the predictable mathematical output of a specific legal architecture. This framework contained 3 distinct vulnerabilities that dictated engine management behavior long before a car ever reached the road. First, a decentralized oversight system allowed for regulatory arbitrage. Second, compliance was measured against an outdated low-load testing cycle that failed to mimic reality. And third, a lack of preemptive disclosure rules shielded engine software from regulatory scrutiny. Combined, this matrix created an environment where designing hardware specifically for the laboratory was the most efficient engineering pathway. Regulators are now correcting these vulnerabilities. The shift toward the worldwide harmonized light vehicles test procedure introduces a dynamic speed profile that replaces the gentle laboratory curves with aggressive accelerations, requiring emission controls to remain active across a wider range of driving conditions. By pairing updated test cycles with centralized market surveillance, authorities aim to finally close the gap between regulatory intent and engineering reality. True environmental protection requires a legal topography that is as rigid and precisely engineered as the physical vehicles it seeks to govern.